Okay, we've been talking about a lot of different chemical terms. For instance, we've used the words like elements and mixtures. So let's take a closer look at those. For instance, we use the word mixture for air. This means it's a combination of several different things that are floating around each other. They are interacting, but they are not connected. This was the nitrogen gas, oxygen gas, and carbon dioxide that we were talking about. These three compounds are floating around each other, but they're not actually touching each other, hence making a mixture. So all matter, you should be asking yourself these questions. Can it be separated by a physical process? If the answer is no, it's a pure substance. But if it's yes, it's a mixture, like carbon dioxide, the oxygen, and the nitrogen can be separated out. If the answer is no, if we look at each of them individually, if it can be broken down into simpler things by chemical means, if you can do a chemical reaction, if it cannot be broken down any further, it's an element. If it can, it's a compound. Let's take a look at what this actually means for us. Here's a picture of a periodic table. Pure substances that cannot be broken down at all. Cannot be broken down by any chemical means at all. Those are the ones that are on the periodic table. Things like we talked about oxygen. We talked about nitrogen. Those are compounds that cannot be broken down because it's a pure element. However, we also discussed carbon dioxide. Notice that it's two words. Carbon dioxide. We have carbon and we have oxide. It's actually a combination of two different elements. So these two things combined are carbon dioxide. And that's what's making it a compound and not an element. So at the periodic table, while you're looking at it, the groups are vertical rows, and these react the same. So for instance, elements over here, these are called the noble gases or inert gases. These do not react. Remember, the word inert means does not react. So the vertical rows react similarly. Horizontal rows are called periods. That has to do with how far away the electrons are from the middle of the atom. And that's beyond the scope of this particular lesson. So this is dealing more with the size. In each of the boxes, you'll notice that there's an atomic number. That's telling us the number of protons. And there's an atomic mass. That's the average weight. There's also the chemical symbol. Some of these are really, really obvious, like carbon is C, nitrogen is N, oxygen is O. Some of them aren't so obvious. For instance, if we take a look at potassium, potassium is K. That's because its Latin derivative is kalium. So potassium is English, kalium is Latin. Another one would be iron, which is Fe. Iron, even though it's written I-R-O-N, its Latin derivative is ferrous. There's also some other breakdowns. You see this squiggly line here, this group, that's a different color. To the right of it is the nonmetals. To the left are the metals. And these in between have characteristics of both. We're going to talk about those later. Alright, so let's take a look at water specifically. Water has both hydrogen and oxygen in it. This is called a molecule because there's more than one element here that are bonded together. Chemical formula is H2O, which means that there are two hydrogens, and there's no number written here, so that means it's an invisible one oxygen. So this is the oxygen in the middle, and these are the hydrogens. Notice that we call H2O water and not dihydrogen monoxide. This is because the word water was around far longer than the naming system that we have. Therefore, they kept the common name. The prefix indicates, instead of having the prefix indicate the quantity of atoms, while the letter indicates. When we're looking at the molecule H2O, the numbers tell us how many there are. The chemical symbol tells us what it is. A molecule is a fixed number of atoms held together by chemical bonds in a certain spatial arrangement, which basically means that there's energy that are keeping these things together in a specific shape. Chemical formula is a symbolically represents the type and number of each element. So here's the number of elements, and that's the type. Many nonmetals occur as diatomic, made up of two atoms. There are only 7 of these. Hydrogen, nitrogen, oxygen, chlorine are a couple of them. Written on the periodic table, we have hydrogen and these here. Those are the diatomic molecules. And iodine. Alright, let's look at the naming. This chart indicates what the prefixes are. For instance, we kept talking about carbon dioxide. Di, if we look here, means 2. So it's carbon and 2 oxygens. Placing one of these in front of the name of the element indicates how many atoms there are. For instance, sulfur dioxide also has 1 sulfur and 2 oxygens. So sulfur dioxide. Notice the di. Once again, the di means 2, so that's sulfur and oxygen. The di means that there's 2 oxygens. Nitrogen monoxide. So if we look at nitrogen monoxide as another example, we have nitrogen and we have oxygen because of oxide. Mono means 1, so N1O1. The first element does not need a prefix if there's only 1. However, the second element, if it is a 1, such as nitrogen monoxide, you do need mono there. Prefixes are used to designate the number and type of elements. Dinitrogen monoxide. Di is 2, mono is 1, so that's why there's 2 nitrogens, 1 oxide. Diphosphorus pentoxide. Di is 2, pent is 5. Notice that they drop the A in penta. If the element begins with a vowel, they usually drop the vowel of the last of the prefix. When these combinations have been altered, a chemical reaction has occurred. This means that the atoms have been rearranged and a new compound has been formed. This is depicted by a chemical reaction. The starting materials or reactants are on the left of the arrow, and the final compounds or products are on the right. Read it like a sentence. You go from left to right, the beginning to the end. Chemical reactions are characterized by the arrangement of the reactants and products being found. Notice here's the reactants on the left and the products are on the right. Carbon plus oxygen yields CO2. CO. Atoms do not just vanish. Like objects in the room don't disappear. Therefore, the atoms there at the beginning on the left are the same as those on the right. We put numbers in front of the compound to even these atoms out. The compound is multiplied by these numbers. If we look at the example above on the screen, there are two in. If we look at the example on the screen, we have to put a 2 in front of the carbon monoxide because the oxygen here. So because of this oxygen being 2, we multiply this whole thing by 2. That means we are also multiplying the oxygen and the carbon. That means we need another 2 in front. Notice that there's 2 carbon atoms and 2 oxygen atoms. Over here there's 2 carbon atoms and 2 oxygen atoms. So here it is used by pictures. We started off with 2 carbon atoms and 1 oxygen molecule. Because this oxygen molecule had 2 atoms here and it got split up, we needed to bond to 2 different carbons. That's why we needed 2 carbons here. Another example is the creation of sulfur trioxide, which ultimately makes acid rain. The coal is burned, this sulfur, which contains sulfur in it. This produces sulfur dioxide, which is right here. Notice dioxide, there's 2 oxygens. The sulfur dioxide then reacts with the oxygen in the air to produce sulfur trioxide. And then that would react further with the water to form an acid. So here it is with pictures. Notice we have 2 sulfurs here. There's 2 sulfur compounds here. That's because of the 2 in front. And oxygens, because we had 2 oxygens here, we actually have 4 here. We have 6 total. And that's where we get 6 here. Luckily, since 1985, we have seen 25% reduction in sulfur dioxide emissions in the U.S. Here's another example. Nitrogen oxides. This is what we see as smog in the atmosphere. It's produced by really hot engines reacting with the air around it. Notice that these are both diatomic. That means that over here, in order to balance it out, for instance, we have 2 oxygens here. We need 1 here and 1 here when it forms nitrogen monoxide. That means we needed 2 of these. Same with the nitrogen. Nitrogen here, nitrogen here. We need nitrogen here, nitrogen here. Cars give off smog, which contains nitrogen monoxide. Notice that we needed 2 molecules of nitrogen monoxide because the nitrogen and oxygen on the left are in the equation are diatomic. Nitrogen monoxide is also very reactive. It reacts further with oxygen to produce nitrogen dioxide. Once again, to make the compound balance, we need to multiply the compounds in the equation. For instance, we have we reacting with oxygen, which automatically has 2. So instead of just reacting with 1 nitrogen monoxide, we have to react with 2 of them. That's how we get all the atoms to balance out. Luckily, since the use of catalytic converters, we've actually been able to take some of the pollutants out of the air. For instance, catalytic converters convert carbon monoxide, which is poisonous, over to carbon dioxide. They also reduce the volatile organic compounds from the tailpipes. Those are other organic compounds that are dangerous. We actually remove lead from the gasoline That's why you always see unleaded gasoline, because of the catalytic converters, amongst other reasons. The gasoline actually corroded the catalytic converters when it had lead in it. Plus, you'd be adding more lead to the air. Let's take another look at the ozone layer, or the ground level ozone, the ground level ozone. Ozone consists of 3 atoms bonded together, so O3. Nitrogen dioxide also increases the amount of ozone in the atmosphere when the sun is out. So notice that it starts off at 6 a.m. and goes to 10 p.m. Notice that the yellow spots get bigger and bigger and bigger as the daylight occurs. But then once it gets dark, it goes away. That's because ozone is triggered by the sunlight and the reaction of nitrogen dioxide. The nitrogen dioxide absorbs the sun and it breaks down into nitrogen monoxide. So it absorbs the sun and it forms NO and oxygen. While this single oxygen here then reacts with O2 to produce O3, which is our ozone at ground level. Not the good ozone, the bad ozone. And then once the sun rays goes away, the ozone then breaks down and it reforms the NO2. Let's take a look at this map. This has to do with the ozone, ground level ozone. Notice how big the area is. Just because this is what's called the tragedy of commons. Air is not contained. Pollution is not contained. It floats from one area to another. As a result, the pollution in one area spreads to others. We will have more examples of this later. So essentially, the pollution is created in one spot, but then it goes to many different others. Pollution is not just outside. We also have to think of the indoor pollutants. For instance, incense burning or paint. Pollutants are just as harmful indoors. Things like cigarette smoke can even be carcinogenic, meaning that they cause cancer. Other examples include incense and paint. However, chemists are constantly creating new chemicals and products that reduce these pollutants. For example, instead of having lead paint, they now have latex paint. And they've been adding stuff to it so that way it spreads better and decreases the pollutants. That's the end of the chapter 1 slides and about the air pollutants.